Now let's talk about comparing two proportions. So again, we need a new standard deviation for our difference between two proportions. So notice here we're using the notation for the difference between two proportions. So it's going to be our population, our first population proportion times the 1 minus the population proportion, right? Because that's what our Q is, whatever the P is, which is just our number over the number in the population, that forms our proportion, the number of successes over the number in the population. That's our P, and then of course Q is 1 minus P. So we have that for the first population over the number in the sample, plus the second population done over the number in the sample. Now, of course, if we don't have the population proportions, then we can substitute in our sample proportions, and it's called the standard error, just like we were doing before for the means. So in order to do our confidence intervals and hypothesis tests, we need to make sure that we meet our independence assumption, which means that we need to check to make sure that the data was collected randomly for each sample, that neither one of the sample exceeds 10% of our total population, and that the two groups are independent. So we've got the randomization, 10% independent groups, just like we do for the means. And in addition, the success failure condition. We need at least 10 successes and 10 failures in each of the two conditions. If all of those assumptions are met, then we can run our distribution will follow a normal sampling distribution, a normal model, a Z curve, not a T curve, with the mean at the difference between the two proportions and our standard deviation given by the formulas that we went over. So same formula for a confidence interval. It is the actual sample mean, in this case, that's the difference between the two proportions, plus or minus the critical Z value times the standard error. Okay, so again, the critical Z value we can look up for each confidence interval. Okay, so let's look at an example where we build a confidence interval. Suppose that 734 men were treated with a new drug and 117 experienced headaches. Now, notice that that means from that sentence right there, my N1, the number in the first sample is 734, and then the number of successes would be the number of people that got the headaches, so 117. And then the P1 would be 117 over 734. And I'll let my calculator do what that proportion is for me in a moment. Now, 725 men were in a placebo group and 29 experienced headaches. So that means my N2 is 725 and my X2 is 29. And so the P2 would be 29 over 725. And I'll let the calculator figure out the proportion for me. I want a 99% confidence interval for the difference between the two proportions. Now, notice that I need to check to see, or my conditions met. Was this data collected randomly? And notice that it does not specifically say that, so we'd have to say, we can only proceed with this analysis assuming that the data was collected in some randomized manner. Then we need to check to see the 10% condition. Well, 734 and 725, that's definitely less than 10% of all men. That would be our population here. And then the independence, we have the group of men in one group that were given a drug, and then a group of men in another group that were given a placebo. So those are independent groups. And then at least 10 successes and failures. Well, our number of successes here are 117 and 29. Those are both bigger than 10. And then the number of failures would be this number minus that number. And same here, both of those are bigger than 10. So we meet all of those conditions. So we're ready to go ahead and run our confidence interval. So our N1, let's go to stat, and we're going to go over to the calc, and we're going to go down to our tests, and we're going to go to the 2 proportion Z test, option number, wait, not the test, we're doing an interval. 2 proportion Z interval, right here, option B, 2 proportion Z interval. We'll do the test on the next video. Okay, so my X1 was 117 out of 734. And the X2 is 29 out of 725. 29 out of 725. And we wanted a 99% confidence interval. So we're going to go to 0.99 and calculate. And notice it gives me my p hat here and here. So the first one is 0.159, the second one is 0.04, and there is my confidence interval. I am between 0.07987 and 0.1589. All right, so let's write that down. Okay, so this first proportion was 0.159, and this one was 0.04. And we have an alpha level here of 0.01, since it's a 99% confidence interval, right? 100 minus 99 is 1%, so 0.01. And so our confidence interval that we came up with here using our calculator was 0.0799 to 0.1589. That was our confidence interval. Now notice that these are both positive, so 0 is not inside the interval, so that means there is a significant difference between the groups. The subtraction is positive. I did this proportion minus this proportion, so definitely this proportion is higher, but we can see that from the proportions, right? So we would say, since 0 is not in the interval, there is a significant difference between the 2 populations. And we are 99% confident that men on the new drug will experience between, or actually I should say, not between, we are 99% confident that men on the new drug will experience headaches proportionately more than the placebo. And how much more? Between 0.08 and 0.16-ish, right? That's how many greater proportion of men will experience headaches while taking the drug. Now, we're 99% confident that the true proportion difference lies somewhere in that interval. We don't know exactly where, right? But that's pretty clear evidence that if you take the drug, men will experience more headaches. Okay, guys, this gives you enough to do a confidence interval. We're going to look at hypothesis testing in the next video.